Okay, so we've centered our Haidinger fringes here at the output of our Michelson interferometer. The pattern is the maximum OPD between the two mirrors. By twisting the micrometer, we can have the fringes collapse by decreasing the OPD or expand by increasing the OPD. We'll count 100 changes in the fringes and compare that to our reading on the micrometer in order to determine the wavelength of our mercury lamp.
So we counted the fringes and we calculated the wavelength of our mercury source. And so we used this equation. So our wavelength came out to be 530.8 nanometers. If we miscounted our fringes by 1, how would this affect the error of our calculated wavelength? We just added a 1 to the denominator in the fringe count, and that gave us an error which is 0.9796% of our calculated wavelength. If we wanted an error of 0.1 nanometers, how many fringes would we have to count? And we calculated it to be 5,200 fringes.
For this experiment, we have a sodium doublet going into our interferometer where we'll measure the average wavelength like we did with the mercury lamp. Because the sodium source emits at 2 different wavelengths, there is 2 different fringe patterns that will add up to create a visibility modulation. In the interferometer, we will go over 2 points of minimum visibility to calculate the difference in wavelength of the 2 wavelengths emitted by the sodium source.
We calculated the wavelength of our sodium doublet to be 597. Now that's an average of the 2 wavelengths. So the contrast between the fringe pattern is called the visibility. And by measuring the difference in translation of our micrometer, or the D source, between 2 null patterns, and then repeating that process and averaging the results, we were able to calculate the delta lambda to be 0.41 nanometers. We expected 0.6 nanometers, but this error probably arises from inaccuracies in where the exact center of the null fringe pattern begins.
We know that as the pressure of air increases, so does the refractive index. So here we're using our Michelson interferometer with a pressurized gas cell. We will change the pressure in our gas cell to alter the OPD. So we are able to measure the refractive index of air by comparing the number of changing fringes we see on our index card compared to the known pressure change we see in our gas cell.
We found that change in refractive index with respect to pressure to be 7.84 times 10 to the negative 6. And we got a value of the current pressure from our iPhones, and then we found the refractive index to be 1.000597408.